Today we are solving Pacific Atlantic water flow problem. There is an M cross N rectangular island that borders both the Pacific Ocean and Atlantic Ocean. Pacific Ocean touches the island's left and top edges, and Atlantic Ocean touches island's right and bottom edges. This island is partitioned into a grid of square cells where the value of each cell represents height above sea level of the cell. The island receives a lot of rain, and rainwater can flow to neighboring cells as long as the height of the neighboring cell is less than or equal to height of the current cell. We have to return 2D list of grid coordinates where each coordinate denotes that rainwater can flow from that cell to both Pacific and Atlantic Oceans. So here is an example island, and the same island is represented in 3D over here. As you can tell, the rows go in this way and the columns go in this way. For example, row 0 is 1, 2, 2, 3, and 5, and row 2 is 3, 2, 3, 4, 4. The water can flow from a cell to its neighboring cell as long as the height of the neighboring cell is less than or equal to height of the current cell. Same over here. And we need to return coordinates of each cell from where the water can flow to both Pacific and Atlantic Ocean. Brute force way of solving this problem would be from each cell we do DFS in all the directions, and anytime in the DFS we reach cells that borders with the ocean, we note down which ocean the cell borders with, and eventually when we reach both the oceans we can add this cell to the result. Brute force way of solving this problem would be from each cell we do DFS in all the directions, and anytime a path reach the border cell we note down which ocean that is, and during this whole DFS for that specific cell, if we reach both the oceans, we add this cell to the result. And we continue this process for all the cells. So the time complexity for this would be O of M cross N multiplied by M cross N. So the first M cross N is because we are running DFS on each and every cell, so there are M cross N cells, and the second M cross N is because in each DFS, in the worst case, we might be visiting all the cells. Is there a way to optimize this? What if during the BFS, any time in a path, for example here, and we reach an ocean, for each of the nodes in the path, what if we cached which ocean these nodes can reach? In the future, if we reach any of these nodes, we can just return the cached result. This will bring down the time complexity to O of Mn. But there is a problem with this approach. Let's see what the problem is with this approach. Let me clean up some space. Let's take this graph for example. Let's say we are in the middle of a DFS path for this node. Let's say we have already explored the left neighbors. Now we have to explore the right neighbors. So the neighbor to the right has the height equal to the current cell. Notice the condition is the height of the neighbor has to be less than or equal to the height of current cell. So which is true in this case, and we can continue DFS down this path all the way until we reach Pacific Ocean. So once we reach an ocean, we note down that all these nodes in the path were able to reach Pacific Ocean. Right here, 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 and eventually here. Notice this node was already able to reach Atlantic Ocean following the left path. So now we can add this node to the result. And anytime we come across any of these nodes again, we can directly return the cached result. So the problem here is you may be able to see this specific node can reach Atlantic Ocean by following the path like this. But we were not able to explore to the left of that node because the left of that node was the parent node itself. So in the DFS, we cannot go back to the parent. Otherwise, we will end up in a deadlock situation. So because of this, we could not explore path through the parent all the way to the Atlantic Ocean. So that's why straightforward DFS with caching doesn't work. How can we solve this problem? Instead of doing DFS from the cell to ocean, what if we change the direction? What if we started DFS from the ocean to each and every cell in this direction? Let's clean up some space and work on this graph again. Here's the same graph again. This time we are doing the DFS in the reverse order starting from the ocean. Let's say we start from Atlantic Ocean, and for each DFS or for each ocean we maintain a different cache. So let's say this node borders with the ocean. That means we can reach the ocean from that cell. So we start DFS from that cell and visit all the neighbors that have height greater than or equal to the current cell. Notice the condition is also reversed because we have changed the direction of DFS. So we can visit this cell and this cell. We cannot go any further because the neighboring cell has a height of 6, which is less than 7. So we stop here, and for all the cells in the path, we put them into the cache of Atlantic Ocean because all these cells can reach Atlantic Ocean. So we mark A, saying all these cells can reach Atlantic Ocean. We repeat this process starting from Pacific Ocean. Let's say this cell neighbors with the Pacific Ocean, which means this cell can reach Pacific Ocean. So we start our DFS from here. We go up this path because each neighboring cell has a height greater than or equal to the current cell. Go to left and all the way to this cell. So we add all these cells into the Pacific Ocean cache. Pacific. So now, as you can tell, we have rightly identified both these cells can visit both Atlantic and Pacific Ocean, and we should return them in the result. So this solves our problem. Let's recap what we have seen so far. Now we do the DFS from ocean to cell, and we maintain separate cache for each ocean, and we return the cells that are present in both caches. So that's our algorithm. Let's write code for this. I've copied the example island here. So the Pacific Ocean borders with the left and the top edges, and the Atlantic Ocean borders with the bottom and the right edges. So let's call M and N the dimensions of the island. And the height. And we need two separate caches for each ocean. Let's call them by their name, Pacific and Atlantic. And these are the sets to maintain the cells that this ocean is reachable from. Next, we have to do DFS from all those cells that border with either of the oceans. For I in range M, let's process the cells on the left and the right edge. We got DFS with row number and column 0 for the left edge and column n-1 for the right edge. So the left edge is Pacific and the right edge is Atlantic. So we need to pass the cache for the Pacific Ocean here and the Atlantic Ocean here. Let's do the same for top and bottom rows. So we call DFS on the top row, which is Pacific, for row 0 and column I. And we do the same for the bottom, which is Atlantic Ocean, with row M-1 and I. So when we have all the cells in the ocean specific caches, we just need to find the cells that are present in both the caches. So the way to do this in Python is by finding intersection. So we just have to return the intersection of Pacific and Atlantic Ocean. This returns a set. We just have to return them as list. So now the only thing left for us to do is define this function DFS. We pass the cache, row, and the column number. If the DFS has already been called for this specific cell, that means this cell can already reach the ocean. So let's add this cell to that ocean. Now let's call this ocean. And we are adding the row and the column. So next we need to explore all the neighbors, which are row bottom cell, top cell, right cell, and left cell. These are all the neighbors. If they're out of boundary, we don't have to process those neighbors. Or if the neighboring cell is already in the ocean, we don't have to process them. Or if the height of the neighboring cell is less than the height of the current cell, we don't have to process them. This is because we reverse the direction of DFS. Now the neighbor has to be either less than or equal to the height of the current cell for us to continue DFS. Otherwise, we don't have to process those neighbors. Finally, we call DFS on the neighboring cell. So that's our code. Let's try to run the code. We pass both the test cases. Let's submit the code. As you can see, this is the most optimized approach. If you found this video to be helpful, please like the video and subscribe to the channel. I will see you in the next video. Thank you.